Good evening, everyone. Thanks for joining us tonight for our stargazing lecture all about dark matter on the day after the summer solstice. I'm Dr. Cameron Hummels. I will be your MC for tonight. And so it's, as I said, it's the day after the solstice. So the sun doesn't set until like 10 minutes from now. So after Jacob's talk, we'll have the telescope set up, and hopefully we'll be able to see the new nearby supernova that's in the Pinwheel galaxy, M101, but we'll just have to wait and see depending on the light conditions. We'll also have views of, I think Mars, Venus, and the Moon are all in pretty decent locations to be able to see, and there'll be some other dark sky, deep sky objects to look at. So just a quick layout of our schedule for tonight. In a few moments, I'll introduce our speaker, who is going to speak for about 30 minutes or so on the topic of dark matter throughout the universe. And after that, we'll take a handful of questions from the audience, and then we'll kind of break, and we'll bring out this table and have a panel Q&A going on, consisting of our speaker, myself, and two other members of the department who work on different areas of astrophysics research. And at the same time, we'll have the telescope set up on the adjacent fields just out here on the athletic fields. And you're encouraged to go back and forth as you see fit. The telescopes will be set up until about 9:45 is when we're going to shut them down. But honestly, the later you go out there, the better, because that's when it'll be darker. And we'll be in here until 9:45, 10-ish as well, answering questions. So you can go back and forth between the two as you desire. The way to get to the field is just go out the way you came, go around the corner, and there are signs that lead you. It's about 100 feet behind me is the entry onto the fields. And let's see. So these stargazing lectures happen once a month. Except this month, we have two in a row. We have tonight, and we also have an event that's occurring next Friday night. It's a special event to coincide with I can't really talk about it, but a major announcement is going to take place involving merging supermassive black holes. There's going to be a press release and all sorts of things. So you'll probably read about it in the news, but there will be a number of members from the nanograv team that's looking for gravitational waves from merging supermassive black holes will be present and on the panel, and one of them will be giving the public lecture next Friday at 8 o'clock here. So I encourage you to check it out. It'll also be live streamed on YouTube, just as tonight's event is. Hello, YouTube audience. And so you can catch it there, or you can catch the recording afterwards as well, if you desire. Let's see, what other announcements? We have a sister series of events called Astronomy on Tap that take place at a local bar in Old Town Pasadena called the Dog House. It's an outdoor patio. You can get burgers, you can get beers. It's all ages, so children can attend. They obviously can't order beer. But we have a couple of 15-minute informal science talks that are given by local researchers here at Caltech and at JPL and various different science institutions in the LA area. We have astronomy-themed pub trivia. It's a lot of fun. I recognize some people in the audience as members who've attended that as well, so it's really fun. Our last one a couple weeks ago was our 100th event, which was super fun. But our next one will be July 17th, Monday, July 17th at 7:30 p.m., and it'll feature two scientists from the NASA Jet Propulsion Laboratory talking about this new mission that you'll probably read about in the next 2 weeks in the news. That's a European Space Agency mission called Euclid that's going into space. It's supposed to launch on July 1st, just a few days away. And it's going to go into space and study dark energy throughout the universe. And so in addition to dark matter that we're going to hear about tonight, dark energy is something we know even less about, but it should be, hopefully with the advent of this mission and other similar missions, we'll learn a lot more. But those two project scientists will be talking about that mission. So I encourage you to check it out if you're interested. And I think those are all of my announcements. So that leads me to introducing our speaker for tonight. Our speaker originally did his undergrad at Peking University in Beijing, China, and joined the department here at Caltech about 5 years ago, working actually in the same research group that I work in, doing some really interesting stuff on the implications of different dark matter models and computational simulations of structure formation and how galaxies form in the universe. And he just defended his PhD last month, so he is now a doctor. I know, it's a big deal. It's a big deal. And so I am very happy to introduce, let's see if I don't mess this up, Jacob or Xuejian. Xuejian Shen. Forgive me, my Mandarin is not very good, but please welcome Xuejian Shen.
Thanks, Cameron, for the introduction. And hello, everyone. My name is Xuejian Shen. You can also call me Jacob. I just graduated here at Caltech and earned my PhD in physics. I'm now a temporary postdoc researcher in the department before moving to MIT. I mainly work on numeric simulations of galaxy formation in our universe. And I try to use these simulations to test the fundamental law of nature. And my talk today will be about dark matter. It's an invisible and mysterious material that scientists believe to exist and fill the entire universe. It is everywhere. In fact, even in this room, there is about 10 to the minus 21 gram of dark matter. And that sounds like a really small number, but if you apply this to the entire universe, that's really a lot. So on very large scale, the universe, the majority of the mass in the universe are in the form of this dark invisible matter. And they are so important for essentially the formation of any structure in the universe. And in this talk, I will briefly talk about the history for the discovery of dark matter and many supporting evidence for its existence. And then I will talk about several popular scenarios about the true nature of dark matter. Sorry, Cameron. Yeah, I need to switch to the next slide. Yeah. Oh, yeah. Sorry. Yeah, our journey will start from the Andromeda galaxy, which is a close companion of our Milky Way. It really shares a lot of similarity to the Milky Way. It has similar stellar mass and similar disk-like morphology. And the only difference is that we can look from the outside. And the Andromeda has been studied for centuries. But in the 1970s, a group of scientists led by Dr. Vera Rubin did a fun observation of this galaxy. They charted a few tens of young star clusters in this galaxy. And these young clusters, the nebula in these star clusters will give rise to emission lines. And by measuring the Doppler shift of these emission lines, the team can measure the velocity of these young star clusters with respect to the center of this galaxy. And the rotation velocities of these young star clusters around the galaxy at different distances are known as the rotation curves. The Kepler law tells us that the rotation velocity of an object on a circular orbit around some mass reflects the amount of mass within the radius of its orbit. And what's surprising about this galaxy, the Andromeda, is that the inferred mass from the rotation velocity of the stars are much larger than the mass of the visible stellar content. And it's true especially towards larger distances to the galaxy center. And this finding is later supported by the radio observation of the velocity of the gas in this galaxy. And it shows a similar story. And there has to be some hidden mass in the Andromeda to explain the large rotation velocity of gas or stars. And this peculiar phenomenon is not just limited to the Andromeda, and essentially every disk galaxies in the nearby universe have large rotation velocities at their outskirts, and they cannot be explained by the visible stellar content. And there has to be something invisible that can extend to larger distances and are even more massive than the galaxy itself. So based on these observations, Nowadays, scientists believe that the real Milky Way is actually surrounded by a halo of this invisible matter, known as the dark matter. The dark matter halo is much larger and more massive than the galaxy itself. It can hobble, it creates a hobble for the formation and evolution of the Milky Way galaxy. The evidence about dark matter is not just limited to the Milky Way-like galaxy. And essentially all the galaxies in the universe, from the low-mass dwarf galaxies to the massive galaxy clusters, are hosted by dark matter halos. And here on the left is an image of the Coma galaxy cluster, which is one of the nearest galaxy cluster at about 300 mega light year away. It's very massive. It's more than 100 times the mass of the Milky Way. And in 1933, the Swiss astronomer Fritz Zwicky, who was working here at Caltech by the time, measured the velocity of individual galaxies in this group. And then he again used some dynamic theory to infer the total mass of the Coma cluster. And he derived a shocking number that the total mass is 400 times the visible mass there. And the number itself was then proved to be wrong, but it still marked the first evidence about some unseen mass in our universe. And the more compelling evidence about the existence of dark matter in galaxy clusters came later through gravitational lensing. And the Einstein theory of general relativity tells us that the existence of some matter will perturb the geometry of space and time around it. And here in this cartoon, the perturber is a black hole. But similar thing applied to a dark matter halo. And this perturbation will deflect the trajectory of the light from a background source passing through this foreground perturber. And the bending of the trajectory of light is very similar to the trajectory of light passing through a classical lens. So that's why it's called gravitational lensing. So if you look at this background source through the lens, the image will be a little bit distorted. And the level of this distortion contains the information about the mass in the foreground. On the right-hand side is an image of a galaxy cluster taken by the Hubble Space Telescope. And you can see that some galaxies, the images of some galaxies are distorted or even elongated to more like a stream-like shape. And these are background galaxies whose light are deflected by the mass in the foreground galaxy cluster. So gravitational lensing provides a good way to measure the mass, the total mass distribution in galaxy clusters via only gravitational effect. A strong proof of dark matter came from the lensing observation of two post-merger clusters. They are known as a bullet cluster, since it looks like one small cluster gets shot through a massive one. And gravitational lensing is not the only way to probe matter in galaxy clusters. Since these clusters typically have very deep gravitational potential, when normal gas flow into these clusters, they're moving at extremely large velocity. And when they collide with each other, they will be shock heated to extremely high temperature, usually much above 10 to the 6 Kelvin. And these hot gases are completely ionized. The free electron and protons in these gases can give rise to very strong X-ray emission. So that's why X-ray observations provides a way to trace the distribution of normal gas in the cluster. The surprising thing is that if you compare the lensing map with the X-ray image, there is an offset between the center of the total mass distribution with the center of the hot gas distribution. And the gas cloud, when they merge and collide with each other, because gas particles can interact with each other, so some of the momentum are dissipated during this collision. So after the merger, the gas cloud tends to stick in the middle, but the total mass component does not. It just travels through each other kind of freely. This observation suggests that there has to be something hidden, something dark there, that actually dominate the total mass distribution. And this dark component has to behave fundamentally different from the normal gas. They need to have much weaker interactions so that they can pass through each other so fast. And dark matter is not just limited to galactic systems. They are everywhere in the universe. And nowadays, there are multiple observational evidences, including the one that we talked about, constrain roughly 26% of the energy budget in the universe are in the form of dark matter, while the normal matter that we encounter in our daily life only accounts for 5%. So because of this dominance in mass, dark matter is really the backbone of structural formation in the universe. On the right is an image of the dark matter distribution produced in numeric simulations. And here we're looking at a really large scale, which is more than 10 to the 4 times the typical size of a galaxy. And the story of our universe is that there are initially some small perturbations in the dark matter density field. And these small perturbations can grow through gravity. Gravity can pull dark matter together, and eventually they lead to gravitationally collapsed objects, which are the nuggets in this image. They are the dark matter halos. And inside these small nuggets of dark matter, that's where the galaxy born. And these dark matter halos are connected by filaments of dark matter. This filamentary morphology of the large-scale matter distribution really resembles the galaxy distribution that we see in surveys. Here on the top left are the results of real galaxy surveys, and the bottom right shows a galaxy distribution produced by simulations, assuming a dark matter dominated scenario. And they really look similar. And nowadays, this picture that dark matter dominates the universe has become the foundation of building a successful galaxy formation theory. People have even attempted more complicated simulations that aims at model the coevolution of dark and normal matter in the universe and trace the entire process of structure and galaxy formation. And the remarkable thing is that it really works. And just now we're seeing the dark matter distribution, and here we are seeing the gas distribution. So the gas can flow into these dark matter halos, these nuggets, and afterwards the gas will cool down and eventually land in the center of the dark matter halo. That's where stars form and the galaxy form. And here we're seeing the Lyman alpha emission from the young massive stars. And this image shows the gas temperature. And you can see in some of the massive halos, gas are shock heated to high temperature. While in some of the low mass ones, gas can cool down. And this image shows the velocity field of the gas. And eventually, the final image will show the stellar distribution. So at the really center of these halos, that's where the star form and the galaxy form. And this distribution of galaxies really looks really similar to what we see on the sky if we remove the foreground of stars in our Milky Way. And we have so far seen the importance of dark matter and the successfulness of this theory in explaining galaxy formation and structure formation in the universe. But what is actually dark matter? This marks one of the most important questions in modern physics. The first question is dark matter really different from normal matter? And all the matter that we encounter in our daily life are composed of 17 fundamental particles described by the so-called Standard Model. And for example, a hydrogen atom is made of a proton nuclear and an orbiting electron. The nuclear consists of 2 up quarks and 1 down quarks bound by a sea of gluons. So the Standard Model is really a successful theory that explains everything we see in our daily life to everything we produce in large accelerators. However, most of these particles in the Standard Model cannot be dark matter. They simply have 2 strong interactions with each other as needed for this weakly interacting invisible component. And if they are really as abundant as dark matter, we would already see the signals in collider searches or in astrophysical observations. There is one exception, the neutrinos in the standard model, and it actually has been considered as a viable dark matter candidate. And the neutrino is a kind of particle that has very light mass and has extremely weak interaction with any other particles. It is also stable. So it looks quite like a good dark matter candidate. However, the neutrinos are just too fast to be dark matter. I'll say they're too hot to be dark matter. And imagine there is initially a clump of dark matter. If particles in this clump are moving at really large velocity, the clump will be dissolved within a short period of time, actually within the crossing time of these particles. So the minimal size or minimal mass of a dark matter structure that can form initially is regulated by the movement speed of the dark matter particle. Unfortunately, neutrinos move really fast, close to the speed of light. Because they are so light, they're very easy to be accelerated to large velocity. So if neutrinos are really dark matter, then in our universe, there wouldn't be any structure below the mass scale of a galaxy cluster initially. In this scenario, the structure formation will go top down. Basically, massive large structures form first, and then they fragment into smaller structures. But what we actually see in observations is contradictory to this. Structure formation goes from bottom up. Smaller galaxies merge to form massive large galaxies. And on the right is an example of an ongoing multi-galaxy merger recently captured by the James Space Webb Telescope. And if you go to earlier universe, you would find that there will be more frequent galaxy mergers, and these merging galaxies will typically be smaller. It really supports this bottom-up fashion of structure formation. So neutrinos cannot be dark matter. A second scenario that people have considered is black hole, or any compact object at solar or subsolar mass. It is known that massive stars at the end of their life can collapse into black holes, and they could be a viable dark matter candidate because they're basically dark and they typically don't interact with anything. And however, the abundance of these massive compact objects are strongly constrained by lensing observations again. And here we're talking about microlensing. Since the foreground perturber here are black holes, or stellar mass black holes, and they're much lighter than the galaxy cluster that we talked before. So the gravitational lensing wouldn't be strong enough to distort the image of background sources substantially. However, similar to a classic lens, the light from these background sources can be focused, and the brightness will be slightly amplified when a black hole passing through the line of sight of a background star, for example. And this is really a powerful way to constrain the abundance of these floating compact objects. And this diagram shows the constraints of these objects as dark matter. And all these green regions are excluded primarily from these microlensing observations. And basically, the conclusion is that if you assume that the entire mass budget of dark matter is some kind of black hole, then it needs to be below about 10 to the minus 10 solar mass, which is extremely small. And there is no stellar processes that can produce black holes of such low mass. And the only possible scenario are primordial black holes created from the very early universe. They can lie in this window, and they are still a viable dark matter candidate. And now, the most popular scenario for dark matter is that it's some unknown massive particle. And in the simplest model, it's just one single species of particle that only interact with standard model particles on normal matter through gravity. And they also have to move at relatively small velocities as we talked before, to preserve the hierarchy of structure formation. And therefore, they're usually named as cold-dark matter. And the simplest model is really backed by some well-known theories beyond standard model. And one of them is supersymmetry. It's a particle physics theory proposed for totally irrelevant reason to dark matter. And what this theory predicts is that every fundamental particles in the universe has their supersymmetric partner. For example, this model predicts there exists a hypothetical particle called electron, which is supersymmetric electron, as a partner of the standard model electron. And this applies to all the particles that we know. And these supersymmetric particles, they're hypothetical, and we haven't found any evidence for them. And the explanation is that they're usually very massive. So the collider, the large colliders existing on the world now do not have enough energy to produce them. But there are good theory reasons to believe that they exist. And some of them are stable enough to be good dark matter candidate. And this group of hypothetical particles are known as weakly interacting massive particles, shortcut as WIMPs. And in the extremely hot and dense early universe, WIMP can interact with all the standard model particles through the so-called weak force. And it is one of the 4 fundamental forces in nature, and it typically happens between nucleons and give rise to various of decay phenomena. And during this early epoch of the universe, and because the interaction of WIMPs and other particles are so frequent, they can be created or annihilated to standard model particle at very large frequency. So everything is kind of in equilibrium. However, the universe is not stationary. It expands and cools down. Eventually, there will be a time that the annihilation or the interaction rate of WIMP with other standard model particles becomes so small that they simply do not interact with any particle in the rest history of the universe. So that's a time we call WIMP freeze out, because WIMPs are free afterwards. And it is at this point the relic abundance of WIMP are fixed. The remarkable thing about this theory is that the relic abundance predicted matches so well with the dark matter abundance that we infer from various observations. So therefore, WIMP has long been considered as the most favorable dark matter candidate. And there have been numerous experiments built in the last 3 decades in detecting these particles. The idea is that these WIMP dark matter particle can interact through the weak interaction. It's just the probability is very low on Earth. However, if we can grab and condense a large amount of protons or neutrons that can interact through the weak force, we can hope to capture maybe one scattering events between a WIMP particle with a nucleon. And one example of these experiments is a xenon. They built a tank of liquid xenon, which is an element that's very rich in protons and neutrons per atom. And if a WIMP scatters with a nuclear of a xenon atom, it will create a recoil of that nuclear. And this recoil energy can be eventually converted to some radiation or charged particle or heat that can be measured by the detectors around the tank. And there are numerous experiments built in the last 3 decades with a similar design and a similar goal to detect WIMP. But unfortunately, there has been no confirmed signal for WIMPs. And this plot, this busy plot, shows the parameter space of WIMP. The y-axis is the WIMP nuclear interaction rate, or you can interpret as interaction probability, versus the mass of WIMP. And all these individual lines are exclusion contours. So basically the parameter space above these lines are excluded. And the conclusion now is that the parameter space of WIMP, originally of interest, is completely ruled out. And there are survived models, but require some non-trivial tuning of the model to escape all these constraints. So that's why scientists start to give up the hope to detect WIMP, and they start to look for alternative dark matter candidate. And in this talk, I want to talk about one alternative model, and it is dark matter with some self-interactions. And unlike the simplest WIMP we just talked about, self-interacting dark matter would require at least two species of particle: the dark matter particle themselves and a low-mass dark force mediator. And their relationship is more like an electron with respect to a photon. And a photon is a mediator of the electromagnetic interaction between electrons. And these two species of particles, they together form a so-called sector. It's kind of an independent group of particles featuring a new fundamental interaction, fundamental force in nature. And this configuration allows dark matter particles to scatter with each other, and the force is mediated by this carrier. And these microscopic scattering between dark matter particles can actually affect the global structure of a dark matter halo. And one mechanism that enables this is thermal conduction. So imagine you have a hot layer of dark matter, which are moving at relatively large velocity, and they have large kinetic energy. And then you have a cold layer of dark matter with relatively low velocities. And because of this dark matter scattering, you can occasionally have particles that cross the boundary of these two layers. But whenever that happens, it will carry some of the net energy from the hot layer to the cold layer. And if this is happening across the entire boundary, then this becomes a way to transfer heat from the hot part of dark matter distribution to the cold part. And here's an example of how this thermal conduction of self-interacting dark matter affect halo structure. Here we're looking at the distribution of dark matter in simulations. And from left to right, we're seeing models, the cold dark matter with absolutely no self-interaction to strongly interacting dark matter. And in cold dark matter, you can see that typically there will be a cusp of dark matter formed at the center of the halo. And these dark cusps are usually very cold, and particles are moving at relatively low velocity, and they condense to the center. But if you have self-interaction, this thermal conduction will drive heat transferred from the outskirts of the halo towards the central part of the halo. And this additional heat brought to the center will dissolve this central dark matter cusp and help form a core. And in observations, there are even some evidences for cores at the center of a dark matter halo. Here on the left is an image of a diffuse dwarf galaxy. And the dwarf galaxy are low-mass galaxies. Their stellar mass are much smaller than the Milky Way. They usually appear to be very faint and diffuse on the sky. And their stellar mass to halo mass ratio are much smaller than Milky Way, which means that they are very dominated by dark matter. So by studying the structure of these dwarf galaxies, we can better constrain the property of dark matter. And scientists can measure the velocities of individual stars, member stars in these galaxies, or measure the rotation of the gas content in these galaxies. What they find is that the mass distribution at the central part of these dwarf galaxies are usually cored, and they tend to agree better with the self-interacting dark matter scenario. Basically, you don't find this concentrated dark cusp as found in the cold dark matter scenario. So this is kind of a hint for maybe dark matter have some self-interactions. And I will end my talk by showing how open the theory space of dark matter is. And we really have a zoo of dark matter candidates that can span more than 80 orders of magnitude in mass. So the lowest candidate are called ultralight dark matter. They can be as light as 10 to the minus 22 eV, which is about 20 orders of magnitude lighter than an electron. So if you have a particle that light, they actually behave more like wave instead of particle. And on the massive end, we have primordial black holes that we talked before. They are close to the mass of 10 to the minus 10 solar mass, and it's roughly 1/10 of the mass of the moon. And showing this large mass range is really kind of a minimal way to parameterize dark matter models. There could be more complicated scenarios such that dark matter have self-interactions, or they could have some residual interactions with the normal matter as far as we can constrain. So the conclusion is that we are still far from knowing the true nature of dark matter, despite the strong faith about their existence. Dark matter has essentially been the foundation of the theory of galaxy formation and the theory of the universe that we have now. So it's really urgent for us to know what is dark matter, and it will continue to be a challenging science question for the community in the next few decades. So thanks a lot, and I'm happy to take any questions.
Are there any questions for our speaker? Any questions for our speaker? Yeah.
Hi, thanks for the wonderful talk. So you mentioned a lot of models, a lot of wonderful models to test different hypotheses. But in general, if you have to do a simulation, what are the assumptions that go into it? Because you said there are so many candidates and we don't exactly know. So, let's say like matter and dark matter is mixing, there has to be some density, some kind of, velocities or something like that. So what are those things?
Yep.
Just wanted to know.
So most of these models would, like most of the simulations, including the one that we see, assume that dark matter is cold, which means that there are some collisionless particles that only interact through gravity. And they're actually quite easy to model in simulations, that you just putting a bunch of particles there and model the gravity of them, and that's it. And the initial condition I did not mention in my talk can be precise constrained by the so-called cosmic microwave background. So that's kind of a snapshot of the matter distribution in the universe at the epoch of recombination. That's an epoch when the free electron in the universe and the proton recombine into hydrogen atom. And afterwards, the photon escape and become basically photon freeze out. So by collecting the photon traveling from that epoch, we can know what's the matter distribution by that time. So this provides a way to set the initial condition for our simulations. And then this initial distribution of dark matter, that roughly you assume some simple properties of dark matter and you let the simulation go. That's what most of the simulation do, for galaxy simulation do. And they assume this cold dark matter model. And of course, you can add some additional physics like the self-interaction, and you can model the collision and scattering of dark matter particles in your simulation. And that's what has been done, for example, in this work. And there are even more exotic models, for example, the ultralight dark matter, because they behave more like waves, and they have quantum mechanical effect on astrophysical scales. So then you have to solve the Schrodinger equation on the entire universe. So there are different ways to model different models, but cold dark matter is really the backbone of most of these simulations.
Right here in the front.
Thank you. Wonderful presentation. I had a question about does dark matter evolve? Where does that come? You had mentioned a white dwarf, and there are areas of dark matter surrounding a white dwarf. And is there like a evolution of dark matter? Where does it? I mean, we kind of touched on the genesis, but what happens, and can dark matter become light matter, and can it evolve over time? And can all these, sorry, now I'm asking like 12 questions instead of one. But is it possible that all of these theories could be true? If that's the case, if there's different states of dark matter?
Yeah, that's a very good question. I mean, so in terms of the evolution of dark matter, first off, the total budget, the total mass budget does not seem to evolve over time. Basically, the constraint you get from these local observations are kind of consistent, the observations you derive from really early universe, and they all suggest a similar abundance of dark matter. Of course, there could be some weird thing happening in the dark sector, whether a species of dark matter particle transform in a different species. But the question is, can we really see that? Like, we only can see actually essentially just photon or some neutrinos from the universe. That's the only thing that's the only way for us to probe the universe. So if really dark matter can decay or transform to some standard model particle that eventually lead to photon, then we can see that signature, but we haven't captured any of those. Of course, if dark matter have their transformation within their sector, and that doesn't talk to any standard model particles, then we wouldn't be able to know that from at least direct measurement, direct observations.
So dark matter and dark energy are both described as dark because we can't directly observe them, or we haven't figured out what they are. But is it possible that dark matter and dark energy are somehow connected, or that one generates the other, or that they're not separate, completely distinct entities, but they actually do have something in common other than a word we've assigned to them?
Yeah, I think that could be true.
What are the theories of how that could be, if there are?
I mean, I'm not too familiar with the actual theory. I mean, I have seen some people writing papers about that. I guess the question is, the state is that dark energy does not seem to behave anything similar to dark matter. It's more like a uniform thing across the entire universe. And the only signature we have is about the accelerated expansion of the universe at late times. And the dark energy, I mean, it doesn't have to be some new fundamental degree of freedom or new fundamental particle, new missing object. It doesn't have to be something like that. You can just fix this problem of dark energy by just introducing some constant in your theory, like the cosmological constant in general relativity, and then you can recover this behavior of dark energy. So I think it's still an open question, like whether dark energy also implies that our understanding of the law of nature is incomplete. But dark matter clearly suggests that our understanding of the nature is incomplete, and there has to be something there, something missing, something invisible locally there that we still cannot explain. While I appreciate the effort to try to solve these two problems together, that could be true.
We'll take one more question for now, and then we'll switch to our Q&A panel and take more questions.
I'm very new at this understanding of the dark matter, but I would say, how close, or if there's any evidence of any vibration, oscillation, or spin of that? I mean, explaining dark matter in the models was one thing. How are they completely away from any kind of trying to attack whether it has an oscillation or spin or vibration or sound? Frequency?
Yeah, I think there definitely are models that cares about the spin of the dark matter particle. Like all these supersymmetric particles, they carry different kind of spins. But I don't think there is a way to actually probe that right now. Like we don't even know what is dark matter, right? And if there are certain channels that the spin of dark matter can, for example, affect the decay product, the rate of decay of these particles to photons, then that will matter. And I'm pretty sure, because there are people looking for the decay product of dark matter over the sky using gamma ray telescope. And I'm pretty sure that the spin, probably the spin of dark matter particles will be relevant for the intensity of the signal.
Okay, please thank our speaker for a wonderful presentation. All right, so for those of you who still had questions, fear not, we will address them. So now is the end of the presentation, but we still have about an hour to go. The telescopes are set up on the adjacent athletic field if you want to redirect and go out that way to check them out. We're also going to start our Q&A panel consisting of our speaker, myself, and 2 other members of the department to take your questions. And feel free to go back and forth as well. Keep in mind that there's still some twilight, so the longer you wait to go outside, it may be better observing in about half an hour, for what it's worth. And recall that in 1 week, we have another lecture here at 8 p.m. involving the potential detection of supermassive black hole mergers via gravitational waves.
Sounds familiar. Oh, it's really good. Well, I've done it so far. Yeah, it's so hard. Yeah, honestly, I would love working. And like, some of the other designers they have, it seems like their whole also I mean, honestly, it's working. I'm like, honestly. Yeah, it's such a really cool institution. It's like in the middle of a neighborhood. Houses. So it's like, it's quite nice. They like higher level business start just
One more chair.
It is cool, it's hard. Mine's more the lab was kind
It won't. Go ahead. Watch your stuff behind you.
Anyway, so part of like making targets on
Yes.
anyway,
First time in my life.
Really?
Fantastic. That's why I rushed out there. I'm like, this is my
This is your chance.
seconds I heard that there's 30 people around.
yeah, that's like nice thing. Yeah, that's a long dance. Also, I don't even like. I only like 70%. So it's like not even that much. Like 70%. It's like so tedious.
Sorry, I've set up a whole tripping setup here.
Let me ask her for support. Was it like yeah, about the I don't know. I carry like a taser.
All right. What's that? Yeah, do your speech. I've got to be on the end. Thank you. All right. Thanks to everyone for sticking around. We're going to get started with the panel Q&A. One second. I just want to get everybody to settle down a little. This mic isn't loud enough. Excuse me, people. Thank you. So we're going to get started with the panel Q&A, both our online audience as well as our in-person audience. Thank you to those of you who stuck around. Oh, goodness gracious. All right, so we'll start off by each member of the panel giving a very short introduction, saying their name, which you can also see behind them, as well as what sort of science they work on, to give you an idea. We're happy to take questions about whatever astronomy or physics or space science related topic that you may have. We can't promise to know the answer, but we can do our best to discuss possible solutions to your questions. But obviously we all work on different areas of research, so that we will explain our topics, and that will give you an idea of what we're more capable of answering as opposed to just random stuff. But we can deal with random stuff too. So I'm Cameron Hummels. I am a researcher here working on computational modeling of galaxies and the regions around galaxies, that kind of the galactic atmospheres, so doing big computer simulations of how these things form and evolve over billions of years. Jacob.
And you know me, I'm Jacob. I talk about my interest in dark matter, and actually I'm also interested in studying galaxy formation in the early universe, and try to interpret observations recently captured by the James Webb Space Telescope. That's kind of my second research interest in addition to dark matter.
Hi everyone, my name is Nicholas. I'm a PhD student working in this building, and I'm mostly interested in stars and their oscillations and what that can teach us about their interiors.
I have my own microphone, I'm special. Hi everybody, I am Stephanie Deppa. I am a former planetary scientist. I studied the outer solar system, the icy asteroids that orbit the sun out beyond Neptune. That includes Pluto and its friends. I know there's some opinions about Pluto in these parts. But that was what I did for my PhD. And now I am on more of the communications side of astronomy, working with the Vera C. Rubin Observatory, communicating the science and the technology of the observatory out into the world at large.
Excellent. So now you know what we know, or some of what we know. We're happy to take questions both from an online audience as well as members of the public. And they can be related to Jacob's presentation as well.
Great, because my question's about Jacob's presentation. So you had a spectrum that was 10 to the minus 22 eV to 10 to the minus 10 mass of the sun. And I think of EV as a temperature. So here we are. What is like, what's like, I don't know, the mass of an electron in EV or something? Or what is my mass in EV? I guess that's what I'd like to know. Thank you.
Sure. Yeah. So EV, just in case, let's just make sure we're all on the same page here. So EV is electron volt, oftentimes referred to as an energy, binding energies of atoms, or if you start dealing with binding energies of the interior, like nucleus, then you're talking MeV, a mega electron volt, a million electron volts. But energy is equivalent to a mass. Einstein's favorite, everyone's equation that everyone associates with Einstein, E equals mc squared, basically means that energy and mass are equivalent with the constant of proportionality that's c squared, which is the speed of light squared. So yes, you are indeed correct that oftentimes we think of this as a temperature or an energy, but it is in fact a mass as well.
Yeah.
Sorry, I'm stealing your show.
Exactly, you're right. Actually, I searched for the mass of electron before preparing this talk. And I just want to explain like how low mass is 10 to the minus 22 eV. And I think an electron is about 0.1 eV or below. It's half, 0.5. Half an MeV. Okay, that's great.
Yeah, half an MeV. So 500,000 EV.
Yep.
500,000 EV. So that gives you an idea scale-wise how, when he was talking about ultralight dark matter, it's, a trillion billion times lighter than an electron is. And we think of electrons as being these incredibly low mass particles in the universe. So it's super, super low mass. But yes, I agree. When I saw that, I was like, oh, I think of mass in terms of like kilograms or solar masses if you want to get really big, but I don't normally think in realm of EV or milli or atto or femto EV. Okay. Other questions? Yes.
Thank you. I also had a question related to the talk concerning dwarf galaxies. So I was wondering how the dark matter halos are deduced for dwarf galaxies, because I understand for elliptical galaxies you can use the rotation curves, but how is it done for dwarf?
So different from like a Milky Way, which is mainly rotationally supported, a dwarf galaxy or elliptical galaxies also, both of them are dispersion supported. So you don't have a coherent motion of stars, but you do have this, locally you have velocity dispersion of stars. And this can effectively create some kind of pressure for this collisionless system and prevent it from collapse against gravity, right? So just by measuring the velocity dispersion of the stars in a dwarf galaxy, you can use that to infer like how strong the gravity is in the system.
Yeah, so it's the motion of those stars against each other as opposed to some sort of bulk motion like the rotation.
Yeah.
Yeah. Yeah, a follow-up.
This was concerning the bottom-up versus top-down galaxy formation model. Would the new James Webb observations of really massive galaxies in the early universe kind of change that notion, or is it still?
Yeah, it doesn't change it.
Okay.
It's consistent with what we see with Hubble and other instrument before JWST. Okay. That's just an example of a nice merging galaxy system.
I see. Thanks.
Yeah, we see those, but it just indicates that merging took place, that kind of hierarchical occurred just earlier. Maybe consistent with our models, but maybe a little bit earlier. Go with the physics professor in the audience here.
I just wondered if you could tell us what is the relationship between the distribution of the dark matter and the ordinary matter now and in the past?
Distribution?
Yeah. We see the distribution of the ordinary matter.
Yep.
What about the distribution of the dark matter? How are the two related?
I mean, you have independent ways to measure the distribution of both. And like in most of the galaxies, they are kind of coherent. Like where you see normal matter, you also see dark matter. So that's why there are series that try to explain the existence of dark matter by just modifying the gravity, the law of gravity of normal matter. But in some systems, like the merging clusters, you see this displacement of the distribution of normal matter and dark matter. And that becomes a challenge to like explain this by modifying the theory of gravity. I'm pretty sure there are smart ways to do this, but then those theories would require introducing a lot of degrees of freedom, which effectively behave as dark matter. So that's my kind of naive understanding of that end. So yes, in most of the places, like the distribution of normal matter do trace the distribution of dark matter, but it's not necessarily the case as far as the observation tells us.
So isn't it that regular matter is more like a disk and dark matter is more like a halo?
Yep, that's our belief.
So dark matter is not a disk.
Dark matter doesn't appear to be disk-like. So in my extremely poor illustration, the red is meant to illustrate like an edge-on spiral galaxy, much like, I don't know, the Andromeda Galaxy or the Milky Way. This is kind of like the disk of that galaxy. And then my really smattering of a black circle around it, much like some of the animations that Jacob showed during his presentation, represents kind of the distribution of the dark matter. So we think, and the models like the simulations that show the formation of galaxies and the structure in the universe are consistent with this, because gravity is ultimately ambivalent as to whether or not something is normal matter, baryonic matter like you and me, or this strange dark matter thing. You tend to have baryonic matter, electrons, protons, galaxies and such, form in the center of these much larger dark matter kind of extended systems, which is the halo that surrounds it. But in general, baryonic matter sits in the center of these larger dark matter structures. So you expect that galaxies have this surrounding halo. You expect that clusters of galaxies have this large structure of dark matter that surrounds them. But when you get on the smaller scales like solar systems, stars, even globular cluster systems, like collections of stars, they don't seem to have any missing matter. They don't seem, you can explain their motions purely by the matter that's there, and you don't have to invoke dark matter surrounding those things, because we don't think that dark matter collapses to form these very, very small structures. It seems to be puffier and only forming larger structures on the scales of galaxies or bigger. Is that roughly? Oh, you have the mic. Yeah, I'll let you go for it.
Yeah, I don't know how I got the mic, but I do have a question. It's a wonderful talk, and I have a question about that, which was there's the energy spectrum that you showed of like the dark matter candidates, and I was wondering why the current super colliders that we have or particle colliders don't allow us to rule out basically dark matter candidates that are at energies below the kind of energies we can produce in those collisions.
Let me see if I understand your question. You mentioned why the candidates cannot be lower mass than the energy scale that the collider can reach?
Or just can we use Large Hadron Collider experiments to rule out any subset of the kind of spectrum of various different dark matter mass?
Yes, indeed. I mean, the null results from these collider experiments does put strong constraints on numbers of models, but there are still fairly good chance that dark matter could be as light as a few keV, which is easily accessible with a small accelerator. But those dark matter candidates would have extremely low interaction with any particles that we know, such as a sterile neutrino, and it's kind of a different flavor of neutrinos. And there are models like that existing. But for a lot of other models that does predict strong coupling to standard model particles, yes, the collider experiments provides very strong constraints on those models.
I'm going to throw in a question from our online audience so they don't feel totally left out. Through greater understanding of gravitational waves, will dark matter's nature and composition come to light? Interesting question. Can we gain any insight on the nature of dark matter by gravitational wave observation? Since that's, such an exciting topic in the last 5 years.
Yeah, I think they're fairly, we definitely can learn something about these gravitational wave observations. Like, for example, if there are tiny black holes merging together, that could give rise to kind of a gravitational wave background. And also there's ongoing, I think, an observation of pulsar timing arrays, which is going to take place.
We aren't supposed to talk about
20 or 30 years. We're not.
Oh, in 20 or 30 years.
In 20 or 30
not
years,
in a week. Okay.
Yeah. So there are proposals in looking at pulsars, basically use a pulsar as kind of a arm of those gravitational wave observatory. And then by measuring the timing of these pulses from different corners of the universe, you can kind of constrain just in the line of sight how the space and time are perturbed. And if you have really tiny object like primordial black holes as dark matter floating around in the universe, they could perturb the pulsar signals as well. Mm-hmm. And this could be a way to constrain these massive dark matter candidates.
Interesting.
Yeah.
Okay. One moment.
Thank you. Jacob, I enjoyed your talk, even though I don't pretend to understand half of it. I'm not a physicist, and this will probably be a very stupid question, but could you tell us something about, first of all, the experimental work that the ESA mission that you say is due to be launched shortly is going to attempt? And then supplementary to that, I'd like to ask you, to what extent does the technology of observational astronomy, how far can that go to support what the theoreticians are proposing? Who leads who, basically? And are you limited in by observational capacity or observational technology, or can the observational astronomers look at whatever you want them to look at?
Yes, that's a good question. Actually, about the ESA mission, are we talking about Euclid?
Yeah,
okay.
Euclid.
Euclid, I think it's a telescope aiming at doing a large sky galaxy survey, and that can help us understand the distribution of galaxies in our universe. Well, the major science goal of that is to constrain dark energy. I'm not sure if that has implication for dark matter, but maybe yes. But I would say in general, astrophysical observation is really hard to tell us what is dark matter, to narrow down a single candidate, because there are great chance that multiple dark matter candidates can behave very similarly on astrophysical scales, as far as we can tell. So the decisive clue of dark matter has to come from some kind of particle physics experiments, direct detections, and unfortunately, the good point about astrophysical observations is that it can constrain a lot of models simultaneously. They can rule out models, but unfortunately they're hard to tell us what really is dark matter.
Yeah, I totally agree with that. And yeah, the experiments that are going on are really hard to do. The ones that are being done, the instrument, like the Xenon project that you talked about, these experiments are these massive undertakings and yet haven't been conclusive. And it does, having these null results that come from that does constrain things overall. But right now, I think there aren't a lot of observational constraints to apply. So theorists are just kind of going wild and you can pick and choose. In fact, even in the questions that we've had, people have been like, well, what about this or that or the other? There's a lot of wide open space for the theorists to run because there aren't a lot of observations to constrain that. So,
Are there any galaxies where black matter is missing? And we had Cameron had mentioned, some galaxies tend to have more black matter than others. Solar systems have less. But are there any galaxies that have where it's absent? And would that help to explain what dark matter is, if so?
Yeah. So actually, recently there is a dwarf galaxy observed which seems to have very little dark matter. It's actually a strong confirmation about the existence of dark matter. Because you have some galaxies that appear to have a lot of dark matter, some galaxies appear to not having any dark matter. So it becomes even harder to try to explain this with some modified gravity of normal matter. It really requires a new component of the universe. But the galaxy that's missing dark matter is really a peculiar one. And we have seen, thousands, millions of galaxies in the universe, and the great majority of them have dark matter. And essentially, the stellar mass of these galaxies follow a kind of a tight correlation with their dark matter content. So this really suggests that dark matter is really important for galaxy formation.
So just to add on what Jacob said, these two candidates, that small dwarf galaxies that appear to be deficient in dark matter relative to what they should have compared to all the other galaxies that are out there, were only discovered in the last few years. I think the study was led by Peter Van Dockum at Yale, and there have been a couple of theoretical follow-ups on this, how can you form these weird systems that seem to be missing dark matter? And in fact, one was done by a professor at Pomona College, just east of here, named Jorge Moreno. He was actually on campus today. And this came out in the last 6 months in Nature. And the idea is that these galaxies tend to form in a very different manner. And they're small and they get so close in, they have their orbit. Time for my bad illustrations. So let's say this is kind of the parent galaxy. This does have plenty of dark matter, but then there might be a smaller galaxy here that's orbiting around that larger galaxy. And this particular galaxy gets really close in to its host galaxy, and the host galaxy essentially strips away the dark matter from that system so that all that's left is the normal matter, the baryons, the protons and electrons and such. And it's dark matter that was once there gets stripped away and is left behind in the greater halo of the host, of the parent system. But it seems like it's pretty unusual for these systems to exist without it disrupting and destroying the entire galaxy as a whole. So it's an interesting system, and we're definitely still learning more about these phenomena as we have more observations, but it's interesting.
First, I want to thank you for explaining these complex notions in simple terms. My question is that, is there any topological relation between dark matter and visible matter?
You mean topological relation?
Some feature that is persistent, or I know it's not visible, but is there any research done on this?
On the topology?
Yeah.
I don't know. That's a good question. I don't know topology enough to know the connections that might exist between
this
baryons.
filamentary pattern is related to topology, right? The fact that if we call this the morphology of this distribution, or this qualitative behavior of the distribution of matter in the universe, then the topology of dark matter is really similar to normal matter. If you look at the galaxy distribution, there are a lot of galaxies like tend to cluster in these around these large dark matter halos. And then they're connected by filaments of dark matter. And in the galaxy distribution, you can also see filaments that has galaxies there. So, I mean, in this sense, the topology of normal matter and dark matter really share some similarity.
Yeah, I'm going to make sure everybody gets a question.
I have a question for Stephanie. You said that in your research you studied Pluto and friends. Would you mind sharing maybe an abbreviated thesis statement just so we can have an eyeball into what you were studying? I love Pluto. So.
Pluto's great.
Yeah, Pluto is great. I like Pluto. Yeah, so what I was doing in graduate school was actually using a galaxy survey to search for, study, discover new objects orbiting the sun out beyond Neptune. So we were essentially data mining and repurposing the survey that was really highly tuned and highly specialized for studying galaxies. We were repurposing it, using that data to find new stuff in the solar system. And so basically out beyond Neptune is this region that's called the Kuiper Belt. And it's actually expected to be much bigger than the asteroid belt, but it's so far away, and the objects are, similar size to the asteroid belt, but they're much farther away. They're much fainter and a lot harder to find. And so we know of way fewer objects overall in this region of the solar system than we do in the asteroid belt. And so we understand really well what kind of like gravitational processes, like orbits of the planets, the things that essentially shaped that region of the solar system, sculpted it into what it is today. But we don't know a ton about that. We know some about that region of the solar system, what shaped the Kuiper Belt, but we know of way fewer, like only a few thousand objects out there. And so really, my research group was using this big survey to find more of these objects out beyond Neptune and try to like kind of fill in that puzzle, fill in that staticky TV picture, and try to like get closer to the answer of what happened in our solar system's history that made that region look the way it does. Does that answer your question?
I'm just going to get one question from the online audience here. Travis Ramirez asks, I've heard the best models of the universe are straying away from particle representations of the matter and looking at fluid-like substances called fields. Do you guys represent things as fields or as particles in models and in simulations? And this is a fine question, both from the representation of modeling the fluids like gases, as well as dark matter. And please, I'll let you do it. I'll stop talking.
Yes, I think that's correct. Like the good way to describe fundamental particles are modeling them as quantum fields. And that's the correct way to do this. But effectively on astrophysical scale, like for many of these dark matter models, we don't actually care about their like quantum mechanical behavior, right? And they effectively behave just like a classical collisionless system or classical fluids. For some model, we do start to care about their quantum mechanical effects, and we also tend to model them as quantum field. For example, these extremely low mass dark matter candidate, their de Broglie wavelengths can be comparable to the size of a galaxy. Then it's essential to model them in the right way. And these models can give rise to these quantum interference features that may affect the dynamics of the stellar objects that we can probe.
Excellent.
This is probably going to be a very stupid question. I'm almost too embarrassed to ask it in front of this audience, but it seems to me that your calculations of of the amount of gravity needed to hold these star clusters together in relation to the known mass inside the galaxy depends on your use of fundamental constants of nature, particularly the universal gravitational constant. And my question is, how do we know these universal constants are so constant? And if the universal gravitational constant, say, wasn't under particular conditions, would that explain, would there be a need to explain dark matter? Would that explain the system as we know it?
Yeah, exactly.
Excellent
There are attempts to do that, right? There are attempts in the framework of this modified gravity. Like you just modify the law like of gravity proposed by Newton a little bit, and the law of general relativity proposed by Einstein a little bit, and then can you explain this by without dark matter by just tuning your model a little bit? And I would say it's really hard because of the example that I show of emerging cluster. Because for some of the systems that the normal matter distribution and the hypothetical dark matter distribution are really like coherent, and so that you can explain everything with some modification of these constants or modifications of the theory. But this merging cluster example really demonstrates that there is some non-local effect, right? It's really hard to imagine that you have a gas cloud whose gravitational effect takes place at a different position. And this is really hard to achieve by just modifying some constant, or assume like at some scale, these constant deviates from what we know.
This is my attempt at the bullet cluster. It looks pretty funny.
That's very good.
Some crazy owl face. I wasn't doing this on mic. So one of the things that Jacob talked about in his presentation, he showed a nice image of, it's called the bullet cluster. And I don't know, is that what you were getting at with this? Okay.
Exactly.
So I agree. Look, scientists don't like invoking ghosts to explain the observations of the sky. Most scientists are very uncomfortable with the idea of invoking dark matter, some unseen particle that we can only see indirectly, as a way to explain our equations. And we, we'll be the first persons to throw that away if there's a way to make it work without having to invoke this ether-like kind of business. But it turns out that every attempt to do that has failed, which is why we're still hanging on to the idea of dark matter. There was a question raised online, there is a popular theory called MOND, modified Newtonian dynamics. Did you talk about it in your talk? I
didn't.
Yeah. So modified Newtonian dynamics is the idea that we only have to tweak gravity, Newtonian gravity that's been around for 400 years, just a little bit, and add an extra term that isn't perceptible on the gravitational scales that we're familiar with here on Earth or in our solar system or whatever. And that once you get to galactic scales where we start to see the effects of what we call dark matter, that, you just tweak something in the equation and that allows everything to work out. And people made arguments about this for quite a while, but they haven't really made a lot of arguments about this in the last 15 years or so because of the bullet cluster that, looks like, get rid of this mouth here and this nose, and the whole outline of the head. And that is, you had these two clusters of galaxies that I've here represented, their dark matter components in black. You can, for those of you online, you can look up much better illustrations of this than I'm doing here. But the black is what we know about where the mass of the system is from the gravitational lensing effects that Jacob talked about during his presentation. So this is where the bulk of the actual mass is. It's invisible, but we can figure out where it is based on the lensing effects from background galaxies. And then the red is where the hot gas is that's, again, not visible, but it's seen in X-rays, which is something that we can use our telescopes to look at. And what you notice is these two things moved through each other, or are in the process of moving through each other, like a bullet going through, I don't know, a watermelon or something like that. And dark matter, which we think is collisionless, doesn't interact. It's like taking two snowballs and smashing them into each other. The gas part that does interact is confined in these kind of little funnels because you've slammed two gas clouds into each other, and so they're responding to that. But the bulk of the mass in the form of presumably the dark matter has not deformed at all when they slammed into each other. And they've gone right through each other as though you have these two microphones that I slam past each other, and they don't interact at all. They pass right through the middle of each other.
Extra dimensional?
You could invoke extra dimensions, but you don't really need to. I don't know which is worse, to invoke extra dimensions or to invoke an invisible particle that only interacts weakly with other things. But that's the rough idea. And because of that observation, it's a falsification of the idea of MOND or any kind of slight tweaks to the way we do gravity, the way we've been doing gravity for the last 400 years. It just doesn't hold up to this particular observation. Sorry, that was very hand-wavy, literally hand-wavy, and poor illustration, but that's the general idea.
I'd like to share some thoughts about that as well, to maybe give you some intuition for how I think there's a very easy sort of way to see as a physicist, at least, why dark matter being dark is actually very related to dark matter being collisionless. They seem like very different concepts, but it turns out they're both facets of this electromagnetic force. And so that's kind of weird, right? Like when I say like two blobs of gas hit each other and stop each other because they collide, well, what does that have to do with like electricity or magnets or whatever? But if you think about it, the reason, for example, you don't fall into the floor is because the electrons in your feet repel the electrons in the floor. So it's really an electromagnetic phenomenon. And it turns out that because light's electromagnetic waves, in order to create light or like scatter light or really be visible, you have to interact electromagnetically as well. And so matter, which we can see, also interacts and collides. But because dark matter doesn't interact with the electromagnetic force, you can't see it. It doesn't interact with any light. But sort of as a consequence of that, or like in the same sort of framework as that, they don't interact with each other like in this sort of contact way. And that seems kind of like, at first glance, it seems kind of counterintuitive that those things would be really two facets of the same statement, but it turns out that they're really the same statement.
That's right. Going to the back of the bus here.
So I was kind of wondering, this is kind of similar to the topography question, but I was wondering if like dark matter is similar to ordinary matter in that it has like phases, like solid, liquid, gas, or like what's the shape of it, or how does it take up volume?
Yeah, it could be. Like there are models that actually assume dark matter can form atoms. For example, like you can have some dark proton, dark electron bond by some dark photon. And there could be a phase transition where free dark electron recombine with free proton. And this is kind of a similar phase transition that we observe for the normal matter. But I would be cautious in kind of introducing this new degree of freedom in the model when there is not much evidence about it. But if that phase transition can really give rise to observable effects, then that would be interesting, and that could be a good way to constrain all these models with some complicated structure.
So do you think there could be like dark matter chemistry?
Yeah, very possible. And actually, in one of our recent simulations, we tried to model the atomic cooling in the dark sector, or even the molecular cooling in the dark sector. But some people would call that crazy ideas.
Hi there. Thank you for having this forum. My question, I don't even know if it makes sense, but I'm just going to go ahead and put it out there. As we're talking about dark matter and dark energies, I'm kind of wondering about any discussions or theories about dark forces, like basically like forces that are exclusively applicable to dark matter and not normal matter, like as you know, the normal matter that you mentioned. Just kind of curious about that, if there's any thoughts or theories, you know, about dark forces.
Yeah, self-interaction dark matter that I included in my talk actually has this dark force. So it's kind of a separate group of particles that can interact on their own, and they have their own force mediator, like a dark photon or dark gluon, and these are all possible. That this can give rise to the scattering of dark matter particles that I talk about in my talk. And also these dark forces are also crucial for the production mechanism of these models, these self-interacting dark matter models. Like for WIMPs, I talk about they interact with standard model particles and then freeze out. But for self-interacting dark matter, you could have a similar process that they interact with each other and they can annihilate or be created from each other, and their number density are not conserved if these channels are enabled. But there could be a time when they freeze out, where their interactions freeze out, and all these creation annihilation process stops. And that sets the relic abundance of self-interacting dark matter. So this dark force becomes really important ingredient in these models to like produce dark matter with the right abundance.
The dark force, I like that. I just started thinking about the Sith, so I'm glad that it didn't devolve into this.
That must always be two particles.
That's right.
For people who are working on galaxy simulations, I'm wondering what are the roles for this kind of work, and what are some science motivations, I guess, for simulation or more computational work?
It's a question about simulating alternative models of dark matter. I think like it's really uneasy to like sit in the situation where dark matter is the foundation of all the galaxy formation simulation, galaxy formation theory, while we don't actually know its property. Like we make really the simplest assumption that dark matter is cold and collisionless, and it's really easy to model. It just have gravitational interaction. But is this really true? Like, is always kind of a question floating in our mind. So that's a good reason to try these alternative models. And also, there are some observational signatures that suggest maybe dark matter is not that simple, including the dwarf galaxy observation, where people find that the central part of dwarf galaxies are usually cold, like they're less dense than what we predict with cold dark matter. And there are other evidences, like by observing the satellite galaxies of the Milky Way, and they also find that the velocity dispersion of these satellites are kind of too small compared to what's produced in the cold dark matter scenario. So they kind of all suggest that the low mass structures in the universe are somewhat less dense than what's produced in a real universe. And all these things kind of motivate us to explore models that can better explain what we observe.
And I'd even expand on that to make it more of a general question, and that is, why do we run computer simulations about any kind of astrophysical system? And that is to really prove to ourselves that we understand the dominant physics that's occurring in those systems. So even in the absence of the concern about different models for dark matter, I think it's important, and it has been important for our understanding of how galaxies form and why they behave the way they do, to try and model that on a computer, to put in the relevant forces that we think are important, and maybe remove some of those and see if the behavior changes, or if it still is able to reproduce the kind of galaxies that we see in the sky. Or not just galaxies, but stars. Can we model a star self-consistently on a computer to prove that we understand what's going on in unseen parts of the star over much longer timescales than we're capable of witnessing, or planetary systems. I mean, people model the behavior of the orbits of the planets in our solar system to see if they're stable on the billions of years that we've been present, or if one goes flying off, or, I mean, even that has constraints on the behavior of gravity on smaller scales. So I think I'm biased because I do computational modeling, but I think there's a lot of utility in trying to model physical, astrophysical, but also just physical systems on a computer to prove to ourselves that we have some understanding of what's going on. Yeah.
Just real quickly, because the simulations and computation to astronomy and astrophysics is like experiment is in most other fields of physics. We can't create another universe in a lab. So computers for astronomers and astrophysicists are the lab. That's how we run experiments. It's just we only have one universe to look at. And so the experiments are to test against what we see when we look out.
Absolutely. Absolutely. We can't and we shouldn't create new universes. I'll get to you next, but first.
So I have a question. I was just curious, is there more than one type of dark matter?
More than one type of dark matter.
Yeah, it's possible. Like, theorists, when like one of the model is ruled out, then they will come up with a new theory with this type of particle plus a different particle so that they can evade the observational constraints. So there are many examples of this.
I was wondering about the stellar oscillation stuff. Why do stars oscillate, and can we observe these oscillations? And by studying these oscillations, what can we know, or I guess use it to infer other stuff about the universe? Thank you.
Cool. Yeah, thanks. So I guess I can give sort of the 20-second spiel that Cameron's heard like 8 billion times.
No, it's good. It's a good spiel. It's a good analogy.
Basically, just forget about stars for a second. If you look at a faraway bell tower and you see a bell, just by looking at the bell, maybe through a telescope or something, you can already learn a lot about the bell. You can see the shape of the bell, the color of the bell. It may tell you what the bell's surface is made of, and so on. But there's stuff you can't learn about the bell. Like you're not Superman. You can't see into the bell. But if you think about it, I think you'd find it believable that like a bell like has to be hollow to sound good. Like if a bell were solid, it would sound awful. And so somehow you realize that if someone rings the bell, somehow indirectly you learn about the interior of the bell, like which is invisible, right? And you can even do that if you, through a telescope, like maybe the bell's so far away you can't even make it out, but you can still learn about the inside of the bell by listening. And so stars do this same thing. They ring for a variety of reasons. And that ringing leads to things like the brightness of the star changing over time. And so if you just watch a whole bunch of stars with their brightnesses changing over time, and you just listen to like what notes are being played by those stars, you can't see the surfaces of, you can't make out features on the surfaces of the stars. They're so far away, but yet you can still measure things like their masses or the structures of their interiors just by measuring the changes in their brightnesses. Stars ring for a variety of reasons. So stars like our sun are called solar-like oscillators. And the reason they ring is because the outer layers of the sun have these big blobs of gas that constantly move up and down, and that causes ringing. And then there are also things like classical oscillators like Cepheids and mechanisms such as like, basically, let's see, how do I explain this? So basically, there's an interplay between sort of changes in the opacity or sort of like the ability, the transparentness of the stellar layers and their feedback with the temperature of the star, essentially, can also cause oscillations. And so it's really a gateway to learn about, I guess, sort of solve a lot of stellar puzzles involving our understanding about the interior of stars, which we cannot see, but which is very vital in our understanding of stars, which are one of the most important objects in astronomy.
Thank you. Appreciate the forum. I just wanted to revisit the topic of MOND for a second. So I was curious, A, is there a respected minority view in the field that still holds to MOND despite the bullet cluster and this evidence, A? And then B, I was curious, could it be the case that both things could be going on? There could both be a modification of Newtonian dynamics and there could be dark matter. Is there anything that would rule that possibility out? And that's why it's so confusing, because there's multiple things going on. All right, thank you.
Interesting idea. There are a handful of people hanging on to MOND. There was a paper that came out.
Yeah, there are even
a month
people
ago,
like giving colloquium here about
really?
MOND. Yeah.
Wait, this year?
A few years ago.
Oh.
And I think like it's good to embrace all these ideas, and like I would be really excited if there is like a theory of modified gravity that like modified general relativity and Newtonian gravity in a self-consistent manner that can explain all these things. That would be super exciting. I just don't know that exists.
There hasn't really
right?
been one yet.
I mean, I think that this is a separate industry to try to constrain like in which way gravity may deviate from what Einstein's theory predicts. And like using, for example, gravitational waves of merging black holes, and which means that there are many independent ways to try to constrain the theory of gravity. And of course, you could have really little modification of the law of gravity, and in the same time having some missing component, missing particle in the universe that we don't know. Those are all possible, I would say.
Yeah, definitely. I mean, the one thing that I'd add is probably Occam's razor, the idea that you want the simplest thing possible, would not necessarily favor something where you have both a modified gravitational system as well as the addition of the kind of complicating addition of an unseen particle. But I mean, there's nothing that says otherwise at this point, so.
I have a question for Stephanie about the Kuiper Belt, but before I ask that question, I was just going to say there were a few questions tonight, very articulate questions that were prefaced with, this is probably a dumb question, or this is a nonsensical question.
No
and
such
it just,
thing.
Well, it just occurs to me that like this is in the context of a discussion of something we can't see, that at some point somebody had to say, you know, this galaxy is rotating so fast, like this is probably a dumb question, but what if it's not flying apart because there's some invisible thing that we can't, so like, yeah, there's no dumb questions. My question about the Kuiper Belt is, what is our current understanding of how the Kuiper Belt formed? Do we think that it coalesced from the disk that originally, collapsed to form the various other objects in the solar system? Do we think that these are bodies that formed further in and were flung out by, Jupiter or the other large planets? And then if it's the former, it kind of makes sense that there would be a belt, like as you conceive of a belt, like the asteroid belt or the Kuiper Belt. But if it's the latter, what put them there and what keeps them there? I mean, is Neptune massive enough to do that? Does Planet 9 have something to do with it? Or, I mean, what's the story of that?
Yeah, great question. So the answer is a little bit of both. Let's see if I can give you like the 60-second history of the solar system as we understand it. So essentially the short answer is we believe that the Kuiper Belt formed in place, which means all of the stuff out there condensed from the big cloud of gas and dust that formed everything in the solar system. It also formed the Kuiper Belt as it is. But when all of that formed, it was much closer to the sun than it is now. And so essentially what we have been able to figure out by finding a lot of these objects, studying the way they move around the sun, running a whole bunch of simulations to see how we think they've moved around the sun over the last 4 billion years. What we've been able to figure out is that there was some like catastrophic event essentially that happened in the solar system about, I forget the timing, pretty early on. And essentially Yes. So essentially what happened is Jupiter and Saturn entered into what's called a resonance, which basically means that their gravitational effects started amplifying each other. And it's like pushing a kid on a swing higher and higher and higher until they go flying. It's the same sort of idea. But what this essentially did is it wreaked havoc on the entire solar system. So back before this happened, all of these asteroids and comets and things all condensed. There were a bunch of them also in between Jupiter, Saturn, Uranus, Neptune. We know now that there's basically nothing in between those 4 planets. It's pretty empty. There's no like other asteroid belt in between Jupiter and Saturn.
Things trailing them in their orbits, but nothing in between their orbits?
Correct. Yes. And so essentially what we believe happened based on computer simulations and models and these kinds of things is when this resonance happened, all of the giant planets expanded outwards. And then as they did that, they plowed through all of this debris that was left in between, including stuff that was out beyond Neptune. And so what's left of the Kuiper Belt is what formed there, and it kind of expanded outward as all of these giant planets expanded outward after this resonance event happened. And as this happened, Neptune kind of plowed through this Kuiper Belt as the Kuiper Belt was also expanding outward. So it was kind of like over the span of a few 100 million years, it was quite the time to be in the solar system. So yes, that's essentially what we believe happened.
I've just been looking at Venus through one of your wonderful telescopes, and I'm bound to ask, phosphene gas in the atmosphere, possibility of life on Venus, what's the Caltech view at the moment? I know there's a big debate gone on about it. What's the consensus here?
I'm not speaking on behalf of Caltech. I'm not affiliated with Caltech.
That's okay. You are tonight because you're a member of our panel. So.
I think what the conclusion of that was there was some sort of calibration error actually in the data. And so they went back and they revisited the calibrations, basically what the kind of processing you have to do before the data is ready for science. And they found an error that...
Well, they didn't. So it's still a controversy and there's still disagreement in the field. The team that originally made the claim of the detection of phosphene, just to make sure everybody in the audience knows. So there was a claimed detection of a particular gas, phosphene gas, that was present in Venus's atmosphere. And it made a big hubbub because the only other place that we had seen phosphene previously was either associated with it being a result of biological processes on the Earth, or I think they'd also found it in Jupiter's atmosphere, but under very, very different conditions that were not present in the Venus detection. And so in some ways, when this claim was made roughly 3 or 4 years ago, 2 or 3 years ago, something like that, the claim in some ways was like, oh, maybe we've detected the evidence for life on another planet. But subsequent analyses of those results indicated that it was possible. I'm going to do another crummy illustration here. The way you detect these sorts of things is through an absorption feature or an emission feature in the spectrum, which is essentially color or wavelength here, and then intensity, I'll just say I, intensity here. And so for like a rainbow that you'd get through a prism from sunlight, for the most part, is kind of featureless. It has reds and blues and oranges and yellows and such present. But when there are certain forms of gas or different elements that are present, you'll get absorption or emission features at particular colors where there's a deficit or additional light that might be present at a particular color. And that tells you what elements might be present in the thing that produced that light. And in this particular spectrum that was coming from Venus, they detected, I believe, an absorption feature that they associated with phosphene. Now, the trick about this whole thing is it's not a nice plain background like that. Usually the way that you fit these spectra are like, wow, they're all over the place. And then you might find something like that. And it's not entirely obvious how to fit this background from which you're choosing to look for emission or absorption features, where you're looking for bumps or troughs. And so the claim that was made by several other groups on analyzing that group's data was that they overfit the background from which they were then deducing that there was a trough that was present. And if you used slightly different conditions in how you fit that background, then the detection went away. But the group that made the claim has doubled down and holds fast to their claim that they did in fact detect this, which, you know, that's how science goes. You have different groups making different claims, and you at some level will converge. And I think the level at which they definitely will converge is there's going to be 2 missions that go to Venus and will have the ability to detect this gas in situ at the location instead of remotely looking at the light. So the Da Vinci mission is I was just talking to one of the project scientists for it. It's going to Venus. It is meant to launch, I think, in 2029, and it will arrive and, you know, do a few loops and then eventually start taking detections of things in 2030. That should, beyond a shadow of a doubt, settle that. I mean, I know that's like a long time to wait, but that will reveal whether or not the detection of phosphene is actually, and probably a lot more than just phosphene. So
one of those missions lost its funding in the current budget.
Yes.
People should write their. Yes,
so the 2 missions are Da Vinci and Veritas. And Veritas, yeah, it has been sidelined to some degree for a variety of reasons. But yes, I think in the current budget, it doesn't have sufficient funding. So yes, as Brian points out, we can all write our representatives and request that money go back to this very important mission to study the conditions on Venus and potentially make, you know, I guess if there's life there, then this could potentially be one of the most important missions.
Planetary Society's website, and you can write a letter very easily.
Oh, really? I didn't know that. Oh, yeah. I'll share what our audience member just pointed out. You can go to the Planetary Society's website and find out information about how to actually directly write. It's very easy to write your representative for this sort of thing. Planetary Society is great for these sorts of things. So did that? Okay.
I'll also, I haven't followed this story for the last couple of years ever since it kind of like calmed down a little bit. Are they doubling? I know when the paper came out, they had not like really explicitly said that, oh, this is from life. Like the headlines kind of ran with that.
I don't know. I know that they have doubled down on the detection, but I don't know if they're claiming that it's biological in origin. We have a question from a young audience member.
So what does dark matter do?
What does dark matter do, Jacob? Excellent. Thank you. Thank you. I want to know as well.
They do gravity, first of all. Like the most important signature is that they add this kind of additional gravity on all the visible objects that we see in the universe. They could do other stuffs, like they could be like converted to some other particles that eventually become photons, like become gamma rays, and so that we can see. They could have some small charge, like really, really tiny charge, and they can have this tiny interaction with the normal matter as far as we can constrain. And they don't do, if they have a small charge, they have a weak interaction with other matter, with a gas. But at the current day universe, since the density is too low, this typically don't happen that much. But in the very early universe, they could be kind of a coolant for the normal gas. So you can have some energy transfer between a dark matter component and a normal gas component that could maybe explain, that could affect the signature of our stars, like this shift in the hydrogen temperature that we see in the early universe, triggered by the formation of first stars. And dark matter, if they have a small charge, they could cool the gas more and decrease the gas temperature at that epoch more. So they could do many interesting stuff, right? And like whenever there's a strange astrophysical phenomenon, like people would try to imagine and come up with a theory that dark matter do this or do that in addition to gravity. We have seen a lot of examples of that.
Indeed. We'll take one last question. We haven't heard from you tonight.
You mentioned that dark matter makes up 26% of the mass of the universe today. How did it change over the life of the universe? Like 10 billion years ago, was it 26 or something else?
Yeah, so that precise number, like there are multiple ways to get that number. So one way is by measuring the microwave background, like which is like 30.8 billion years ago. And there is kind of an oscillation feature in the kind of the spectrum of the like matter distribution at the epoch of this cosmic microwave background. And just by measuring the strengths of that oscillation, you can constrain like how much dark matter are there by the time. And a different way to do this is by looking at galaxy surveys, because these initial perturbations will grow and eventually they would affect how matter are distributed in the current day universe. So you can do a similar measurements of how that oscillation in the density field behave at the current day mapped by galaxy surveys, and you would get a consistent strength of that oscillation, which means a consistent abundance of dark matter across 13.8 billion years history of the universe.
I lied, and we'll take one more question from an exuberant young audience member.
This question is totally off topic, but I would like some answers to it. So, do you have any suggestions in how to succeed in learning math?
Oh. Suggestions in how to learn at math.
Well,
Oh,
I'm
boy.
not good at math, actually. I mean, I think it depends on whether you really have strong interest in math. I mean, for most of our daily life, you don't really need too sophisticated math. You don't need to solve differential equations.
You probably don't
right?
need to do a lot of integral calculus in your day-to-day life, but I think our audience member is, what grade are you in? Going into 7th grade.
Yeah, I think there's
still a lot of math that I think is applicable.
It's really to appreciate the beauty of math, and like let the interest like drive your study. And I think I really appreciate this.
Stephanie, Nick. Yeah, I would say just practice. Just like I'd recommend for trying to learn anything, mathematics, music, a new language, all of these things, a lot of it is just taking the time to focus. And yes, having an interest or seeing the beauty in that thing can help motivate you, but a lot of it's just putting the work in and spending time doing that thing. Even if you don't necessarily want to do it, you got to keep a regular schedule and keep at it, so that, working on it every day, so it doesn't fall out of your brain after a week or 2 weeks or whatever, if you give it a rest. So I'd say consistent study is really necessary.
Yeah, so I concur with the statement that you should, it's just a lot of hard work. Like, people have this idea that there are people who are just inherently good at math or something like that. But really, math is just like anything else. It's like drawing or you might see a friend who's good at drawing and think like, you must be inherently talented. But what they're not showing you is that they've like spent a lot of time practicing that. And you only really see the final results. And so I just want to sort of hit home that, this is really something that anyone can do. It's just like takes a lot of practice like anything else. And I guess I want to say another sort of hot take thing as well, which is maybe a little bit something that you don't hear all that often, I suppose. But when you're in school, like grade school, I think people often have kind of like a bad math leaves a bad taste in a lot of people's mouths because it seems like you have to follow all of these very strict rules, and then like, you know, if you don't do the rules in exactly the right order, the teacher is like takes off points, and then people feel kind of bad. But I sort of want to instill this kind of perspective that, in my opinion, math is really about breaking rules and like sort of being creative and seeing, you know, what happens when I assume certain things to be true. And so you might have heard in school, for example, that you're not allowed to divide by zero. Well, why are you not allowed to divide by zero? Actually, mathematicians don't think that you're not always allowed to divide by zero, right? Like there are number systems where you can divide by zero. They just behave a little bit differently and they have different rules, and you just have to learn those different rules. But the point of math is not to like stick to this one rigid system. It's to like expand your mind, be creative, and explore how certain things imply certain other things. And that's all it is. It's really a creative thing, and with some hard work and really creativity, you can really thrive in your study of math, I would say.
I'll also say making friends who like math that you can study with together will make it a lot more fun. So if you have a group of friends that you like to do math with, that'll keep you all motivated and keep you practicing more consistently, and then you'll get better and better at it.
Absolutely. All right. I think that brings us to a close tonight. Thank you, everyone, for sticking around. But let's have a round of applause for our speaker and our panelists. As I mentioned, we have a special event next week, this very next Friday at 8 o'clock, the same time as we had tonight's event, featuring a talk about merging supermassive black holes and the ability to detect these in a new way. And it'll probably be pretty exciting. You'll probably read about it in the day preceding this event. So I encourage you to check it out. And our next Astronomy on Tap will be on the European Space Agency mission Euclid with two members of the team from the NASA Jet Propulsion Laboratory, Dr. Jason Rhodes and Dr. Alina Kiesling. And they will be talking all about dark energy and some of the detections that can be made with the new ESA Euclid mission. So check it out if you're interested. Thanks for joining, and we'll see you guys next week.